So I want to start, of course, by thanking the organizers for this fantastic meeting we've all been enjoying. The talk I'm giving here is a pedagogical talk. We've heard a lot of very nice talks already in this meeting about pump probe techniques and about, especially about angle resolved photoemission spectroscopy. But here I'm going to change gears just a little bit. And I'm going to be focusing on core level photoemission spectroscopy. So I'm going to focus on X-ray photoelectron spectroscopy and on the subsidiary technique of X-ray photoelectron diffraction. And I want to talk about these techniques and how we pursue the analysis. And then importantly, because this is the impact meeting, I want to talk about how we're taking these into the ultrafast regime. So I work at the UK Central Laser Facility, but this work I'm going to be talking about is actually, all of these projects are very large collaborations involving very many institutions. I'm just showing a few here. I want to emphasize the leading role that's been played in these directions by two of our impact colleagues, Kai Rosnagel and Philip Hoffman, both of whom spoke last week. And I also want to emphasize the papers I'm going to focus on today were the postdoctoral project of Dr. Davide Curcio, who is now in a permanent position in Trieste, and Dr. Clara Volkert, who was a PhD student in Aarhus University at the time. So I think a lot of us have at least some basic experience with X-ray photoelectron spectroscopy, the basic idea being that you have monoenergetic light incident on some sample of interest, and if the photon energy is sufficient, bound electrons in our sample can be excited above the vacuum level, and if we have some kind of photoelectron analyzer that can discriminate in terms of the kinetic energy, then because energy is conserved in the photoemission process, then because we know the original photon energy, then in the simplest picture, we imagine that we can extract the binding energy of this initial state in our sample. And we'll see that this is somewhat of an oversimplification, but this is the starting point. And then in this picture, we expect that we'll get spectra that look something like this. So this is a cartoon this is a cartoon of gold single crystal 1-on-1 surface, and this is actual data, just exemplary data from the gold 4F spin orbit split state, where you can see photoemission intensity as a function of binding energy. As I'll talk about in my talk here, we can actually derive much more information than you might naively think from this technique. So we can actually extract rich information about the chemistry in a sample, about topics such as magnetism and spin physics, even about electronic states that are close to the Fermi level. And this might seem at first glance naively surprising. A lot of the energy scales of these kinds of phenomena are very, very far from what we think of as the energy scales of these very tightly bound core level photoelectrons, but we'll talk about how this comes about. And the important thing in order to extract this kind of information is to be able to very precisely fit these peak shapes that we get. So the location of these peaks in terms of energy and the shape of the peaks. So of course what we need is we need some good models to understand these intensity distributions. So the one I'm going to focus on for this talk is this one from the 1990s. And here you can see that the photoemission intensity as a function of the energy depends on several parameters, some of which I've started to touch on already. So we have, for example, the width of this peak. So there's a parameter that describes the Lorentzian width of this photoemission peak. This connects to the photohole lifetime in our sample. We have a parameter that is connected to the Gaussian width of our peak. So this is related to phononic excitations in our sample and also our experimental energy resolution. And then we see over here we have a whole other term. And this term is related to asymmetries in the shape of our peak. So this was described in this paper as arising from low energy losses during the photoemission process. So if we imagine that we have a tightly bound core level escaping our sample with a certain kinetic energy, it's possible that there may be some low energy excitations, perhaps electron hole pair excitations close to the Fermi level, that may be excited by this outgoing photoelectron, and these will steal part of the energy from this photoelectron. And this will be evidenced in our spectrum as a shift in the photoemission intensity toward the lower kinetic energy side of the peak. So with this, as I've said, with these kinds of careful fitting, we're able to extract these kinds of information. But we don't want to stop here, especially, as I said, I want to talk about extending these models to dynamical systems. So if we have a very similar setup to what I've been talking about, but we now want to look at systems that are excited in some way. So in this case, in this picture, I'm showing a pump probe scheme where we have an initial excitation with an infrared or a visible pulse. Then we can use a very similar technique, bringing in a second pulse of the photoexciting energy, so this is in the UV or X-ray regime, in order to look at the dynamical behavior of chemical processes as they occur in time, of electron-phonon coupling, physics in the conduction band with time resolution, for example. Of course, this introduces a lot more technical challenges, so now we need to be able to have light sources both in a very low energy regime and also this higher energy regime that I talked about. And we need to have these light sources be such that they produce short pulses. And these short pulses of light need to be well synchronized with a controllable time delay between them so that we can shift the time delay to various delta t values and look at how this excitation evolves at different times after the initial pulse. Of course, our time resolution is going to be limited both by the pulse width, the temporal pulse width, and also by this synchronization of the two pulses. Typically, for many of the types of experiments I'm talking about here, this is something like tens of femtoseconds up to picoseconds, depending on the physics of interest. These particular projects I want to talk about were conducted at Flash, and of course, we can see that a free electron laser is going to be the most sort of straightforward way to achieve these kind of technical challenges. So we have the output of the free electron laser, which in the particular case here comes as these pulse trains, megahertz pulse trains, separated in time with a 10 hertz frequency in between the pulse trains. This is just the pulse structure that's the output of the FEL. And at this beam line, there is a second optical laser, tabletop laser, that is specially coupled to this special bunch structure of the FEL with a delay stage, so that then it's possible to recombine these two beam paths and bring them together to our sample surface. I'm not going to talk a lot about the photoelectron detection, but I'm more than happy to talk about this in the question session if people are interested. But we use this time of flight momentum microscope. The important thing here is just that we're discriminating the kinetic energy on the basis of the time of flight that's required for the photoelectrons to move through a field-free drift tube and eventually arrive at our detector. The detector is simultaneously collecting all photoemission angles. So let's look at a simple model system. Graphene. So here in the center, you can see actual data acquired on the beamline. So here, the horizontal axis is showing binding energy. The vertical axis is showing time delay, with 0 being the time 0 at which pump and pulse arrive together. This is the pre-pulse domain. This is the post-pulsed regime. And you can see in false color then the photoemission intensity. And you can sort of see by inspection, that there is a relatively sharp peak that somehow broadens and then becomes sharper again. And you can see this better yet if you look at this different spectrum with red, white, blue as the positive to negative difference spectrum relative to the pre-excited case. So here you can see a bit more clearly that our photoemission peak broadens with weight moving to the tails, and maybe the asymmetry changes, and then we have a restoration of the initial peak shape over some few picoseconds. But now, in order to understand what's really happening, we need to make some changes to our model. So in the model I already showed you, I talked about these low energy losses that can occur. But now we have a situation where we already have a highly excited population of pumped electrons in the conduction band. And now it's quite possible that our escaping photoelectron may either lose energy or gain energy from this excited state electron population. So we need to be able to account both for losses or for gains that occur in this process. Also, we have this basically joint density of states term here. In the original model from the 1990s, this was assuming a state at equilibrium at 0 Kelvin, but that's presumably no longer a very useful approximation now in this highly excited regime. So we are going to want to account for finite temperature in our population of electrons. So we can rewrite this joint density of states in the way you can see here, and we can also adjust our limits of integration in order to account for both gains and losses in our photoemission process. I would just note here that by taking the Fourier transform of this second term, we get what's called the asymmetry kernel, and it's shown here in green, and this gives us sort of a nice, very intuitive picture of the degree of asymmetry in a core level peak like the one that's shown here in red. So I'll be referring to this throughout the talk. And so what we would expect then with this new model, sorry, let me go back, is that now we're going to see a reduction in the asymmetry with pumping because of the fact that we can now either, sorry, this is somehow doing something weird with an animation, that we can either lose or gain kinetic energy when we're in this highly excited regime. And this is indeed what we see. So here we're seeing cuts, we're seeing spectra taken from these various time delays, shown here, just some exemplary time delays. There's nothing special about these times. This is the initial state before the excitation with a very strong asymmetry, which you can see here from the asymmetry kernel in green. The red is showing the data itself, and it's actually quite hard to see because the fit is very, very good. So this blue line on top of the red is the fit. And then after pumping, we see a strong broadening in the peak, a very significant broadening, and a reduction in the asymmetry. And then, over time, a restoration of the asymmetry and a sharpening of the peak. Now, this model gives us directly the temperature of our electrons. And these temperatures are quite consistent with what we would expect on the basis of previous work done using different techniques, for example, ARPES. Indeed, what we expect, this is an identical sample system to ours from an earlier paper based on ARPES, is that with the initial excitation, we have excitation of carriers within the Dirac cones of the graphene. We have a very, very fast thermalization that's on a faster time scale than we can resolve in our experiment, so that by the time we make our measurement, we already have a thermalized electronic population where we can legitimately talk about this temperature of the electron population. And then we have a coupling, strong coupling to optical phonons in the system, which gives a relatively quick decay, or let's say reduction in the temperature of the electrons, the excited state electron population. And then at some point, we have a bottlenecking effect and a subsequent very slow decay wherein there needs to be super collision events or coupling to acoustic phonons, which is a very slow process. We can compare our data, which is seen here with these red dots. This is the data that we obtain from the fitting of the core level, as I just discussed, to models previously derived from other approaches. So using this 3-temperature model derived from this paper I just referenced, we can consider how the energy in this electronic system decays through coupling to optical phonons and acoustic phonons, and the resulting changes in the temperature of the optical phonons and the acoustic phonons here. And you can see that the fit from this 3-temperature model is a very good fit to the actual data that we observe, as is a simple fit from the Fermi edge of our sample. I would also just mention that this particular fit using this 3-temperature model yields, with our temperature, this fit, this red line here, gives us a very good set of values for the electron-phonon coupling constants, which are consistent with the previous literature as well. Okay, so this is just an example from a sort of simple, somewhat well-understood system. These experiments are extremely challenging. But what I want to take away from this first part of the talk is the idea that through detailed line-shape fitting, we can, in the first place, extract a great deal of information about surfaces in equilibrium or out of equilibrium. We can get information about all of these various chemical and electronic properties, and then with the aid of pump probe techniques, we can look at the evolution and decay of these excitations in the electron lattice, and we can also make various other kinds of time-dependent measurements. So looking, for example, at chemical changes, for example. Okay, so I want to now talk a little bit more about the physics of these core-level photo emission events, and whether we can use these kinds of spectroscopy to actually get information about the structure as well. So let's set this graphene example on the side, and let's go back to the basic picture of the photoemission process. So if we imagine the situation for our photoelectron leaving our sample, so here's a cartoon. This is just from an older paper I did. The material doesn't matter. This was, in this case, molybdenum disulfide. But you imagine the core level, or the core level photoelectron leaving the sample and going eventually to our detector. You can see that there are many different multiple scattering pathways that this electron can take to get back to our detector. And what this means is that there are going to be quantum interference effects of this electron with itself. And you can sort of quickly see intuitively that these interference effects are going to encode the geometry and the symmetries of the lattice around our emitter. They're going to depend on emission angle, of course, and here I'm just showing the polar angle and the azimuthal angle. If we, from a practical point of view, what this means is if we look at some particular peak, so looking at the case of this sulfur emitter at the top of the layer, we look at the 2p core level states, we look at one of the emitters at the top of this layer, and we sit here at this peak, this pale orange one here, for example, and we now rotate and tilt our sample in front of our detector. We're going to see a modulation in the integral under this peak as a function of angle. And we can then plot this integral as a function of polar angle and azimuthal angle, and you get diffraction patterns that look something like this. Of course, you can see here that there's a chemically inequivalent sulfur emitter as well in this system, and these shifted peaks derive from the chemically inequivalent emitters at the bottom of the layer where there's a substrate. And these peaks will have a completely distinct diffraction patterns, partly because they're chemically distinct and have different kinetic energy, and also partly because they have a different set of forward and backward scattering events that can take them to our photoelectron detector. And here you can see the distinct diffraction pattern, I hope you can see, for emission from this bottom emitter. And then also we can play games by changing our photon energy in order to control the kinetic energy and change the ratio of forward to backward scattering in our measurement, and we can further analyze the diffraction patterns on that basis. In the data that I'm showing you in these slides, the orange false colors the actual measured data. And what we do then is we take the intensity as a function of angle for each one of these points, each pixel. We typically define a modulation function, so this just allows us to regard the intensity relative to some perhaps slowly varying intensity functions that don't arise from scattering. So these may be experimental effects, for example. But you can think of the modulation function as being essentially the intensity as a function of angle. And we're going to then simulate the expected modulation function for a range of different structures. And we're going to compare these to the actual observed data and force these two to converge. So what the basis of the simulations is this electron diffraction in atomic clusters package, which was first described in the early 2000s. Using this, we simulate several test structures, and then we compare in each case the modulation, the measured modulation function to this simulated one, quantifying in each case the divergence with this so-called reliability factor, which is basically kind of a normalized divergence of the two modulation functions. And then we can vary the parameters in a controlled way, and through a gradient descent approach, force the simulation to eventually converge to the actual measurement. So here I want to just highlight a couple of key points. So first of all, I want to emphasize that, I mean, of course, depending somewhat on factors like the photon energy, the kinetic energy, but in general, this is a very surface-sensitive approach. So this makes it complementary to techniques like, for example, X-ray diffraction, XRD, which is a much more bulk-sensitive technique. So this is really a surface science method that I'm describing here. Another very interesting and important detail is the fact that you actually don't need long-range order in your sample to make this work. So if you have, for example, some kind of adsorbate that you want to investigate that is perhaps on a relatively unordered surface, but however has well-defined adsorption sites with local order around them, you'll still be able to draw out this local order with your XPD analysis. So then can we take this to the time domain? And it's sort of easy to see that this is really interesting if one can do this. So you can imagine making dynamical studies of structural changes as they're happening, perhaps like movies of phonon modes in action. And I mean, very interesting for this conference, you can imagine combining the chemical and electronic info that you get from XPS, such as we already talked about, together with the kind of structural information that you can get from XPD. So just to take an example that I think is close to many of our hearts, 1T tantalum disulfide. We've heard some very nice talks about this. So this is a system, as we know, with a low temperature phase with Star of David charge density wave distortions. And in this structure, there are three chemically inequivalent emitters in the tantalum, among the tantalum atoms. And if you look at the tantalum core levels, these will correspond to three shifted, distinct core level photoemission peaks. So here we're looking at the 4F core levels of the tantalum, and there's an A peak, a B peak, and a C peak in the spin orbit split 4F core levels. And this is a subject that was already investigated with this very nice paper from Kai Rossnagel and his colleagues some time ago, looking at using pump probe with XPS to try to understand something about the electronic and phononic effects underlying the melting of this charge density wave. And now we can further imagine that we can bring to bear on this the additional structural information that we can get from XPD. So this is like an extremely difficult type of experiment, but this just sort of motivates the kind of really interesting, complicated experiments that one can imagine doing. And another interesting one is, of course, making movies of surface catalytic processes. So you can imagine a situation where you have maybe some photocatalytic process happening and making movies of the dynamical processes involved, being able to identify adsorption sites and also make use of this chemical information from XPS. So there's a lot that you can do. They're very difficult experiments. Let's just look at another simple model system to show how this works. So I talked about this picture already. Now we imagine that instead of just looking at how this spectrum is changing with pumping at different time delays, we're actually going to look at how this diffraction pattern is changing with pumping at different time delays after the pumping. But the picture I showed you so far was that you have your sample in front of the analyzer, you're tilting it, you're rotating it, and for every angle, you're measuring this spectrum. And this takes many hours, and when we're now adding the additional dimension, the time domain, this is going to become prohibitive. So we're going to need to have some other approach, and fortunately, as I already mentioned, here at the PG2 beamline in this Hextop end station, we're actually able to simultaneously acquire all emission angles simultaneously. So this means we should be able to measure this entire diffraction pattern in a single shot, so to speak, all at once. So this is what we're going to do. So let's take this very simple case of bismuth selenide. This is a system we all know very well. We have the covalently bonded quintuple layers with selenium and bismuth, and these have van der Waals bonding between the layers. And importantly, for the purpose of this test, the phonon modes are very well characterized through multiple means already. The literature is very rich on this topic. And it's known that there is this A11G phonon mode, which is very easy to pump. So you can pump this above resonance. You get some short-lived transient states, which very quickly decay and dump all the energy into this long-lived coherent mode, which is kind of a breathing mode where the bismuth and the selenium at the top of the layer are moving away from the bismuth and selenium at the bottom of the layer. And this has this 500 femtosecond oscillation approximately, which is well within the time resolution that we can achieve on the beamline. Okay. And then the data we get looks something like this. So here is a cartoon of our setup. Here is our quintuple layer. And our detector is here. We have our diffraction appearing all at once, collecting all angles simultaneously, our pump and our probe. And if we look, for example, at our selenium 3D core levels, this is data from both the equilibrium case, so that's this black line here, and also the pumped spectrum, which is the red line. And there's a lot going on here, and I can talk more about it, but the diffraction pattern that we get on our detector is something like this, and there's been a normalization here, but basically this is what we get on the detector. And here you can see a pre-pumped case, and here you get several post-pumped diffraction patterns. And these are just times a bit randomly chosen for illustration. Now, when you look at this with your eye, it's kind of hard to see if anything's happening, but using these simulation techniques I just talked about, we can indeed optimize a structure around the best fit to each of these. And here are the calculations here at the bottom. And here we are leaving free the out-of-plane length, the out-of-plane dimension of this bond length at the top two bonds here between the selenium and bismuth at the top of the layer. And although, as I said, this is hard to parse just by eye, we can quantitatively compare each of these diffraction patterns using a technique similar to what I talked about before. So we define this R factor as one that allows you to compare two modulation functions. We use it to compare experimental and simulated modulation functions when we're analyzing our data, but we can also use it to compare two different experimental modulation functions. So for example, the time zero and the post-pumped modulation function. And we refer to this as the self-R factor. And this is being shown here in this plot, so you can see The red line is just showing the Gaussian broadening with pumping to help us identify the location of time zero. So the time zero is here. And you can see that very shortly after the pumping, we see an increase in the self-R factor corresponding to a change relative to the initial equilibrium diffraction pattern, and then a decay within a few picoseconds as expected with various modulations along the way. And now we can actually directly extract some of these structural parameters. So looking at these D1 and D2 lengths that I talked about, we're actually plotting the divergence relative to the equilibrium D1 and D2 as a function of time. And you can actually already start to pull out, even though this is a very simple system that's well understood, you can start to pull out some interesting subtleties. So, for example, after this initial sort of, as I said, quick decay of various sort of transient modes, we enter this sort of oscillation, this coherent breathing mode. And then what we actually see is, although the selenium and the bismuth are at the top of the layer are moving together like this, actually the change in D1 and D2 relative to the equilibrium values are actually out of phase. So you can see that here. These dashed lines are just showing the time delays I showed in the earlier data, just for specificity. And you can see here that when one is high, the other is low, and when this one is high, this one is low. So basically, although these are moving in phase, the magnitude of the movement for the bismuth and for the selenium is very different, right? And so that means that when the delta 1 and delta t are actually out of phase. So you get already some very interesting little details coming out of this model, even in this very simple picture of this well-understood system. We can confirm the approximate period of the expected oscillation consistent with this softened phonon mode that we would expect to see at the surface, and the magnitude, the expected magnitude of this oscillation. So with this, I'll wrap up. But I think just to highlight once more a couple of the key things. I've shown you some sort of simple model systems. I've talked about how these experiments work. I've talked about how they're very hard, but also I hope I've convinced you that there's really interesting scope looking to the future for these kind of much sort of very ambitious experiments looking at chemical, electronic, and structural properties all together in a single experiment. So yeah, I'll be happy to take any questions anyone might have.